Hey everyone, it's Tyler from CG Forge. In this special edition video, Ian and I decided to do a collaboration where he makes a video for my channel and I make one for his. So in this project, we're going to be exploring optical flow, and we'll be creatively using optical flow to go beyond the typical curl noise or anti-alias noise that you usually see whenever we have objects move along the surface of an object. So in this case, we have mushrooms. They're all moving along the object. With optical flow, we're able to create some interesting organic motion that, again, goes beyond what you typically see on any sort of project that you encounter. So we'll start by talking about optical flow. I'll give you a simple demonstration of what it is, and then we're going to get creative in how we apply it to this awesome tree dude that we see right here. The main idea with optical flow is that we want to take video footage and use that to create velocity vectors that point in the direction of changing motion. If we move forward here in the timeline, we can see that we have this interesting video footage loaded in. And to do that, I made a copnet, and I just used a file cop to load in JPEG images that have been stripped away from video footage. I'll show you how to do that here in a moment, but basically put, we have JPEG images. A new JPEG image is loaded on every single frame to represent the motion here of our video footage. And this is all stored in 2D volumes. If we middle mouse here, we can see that we have one grid volume, and right now the resolution of that is 2048 by 2048 voxels. Now, some of you may not be familiar with what 2D voxels are, so allow me to explain. When we have a voxel, typically that is represented by a cube. So if I just draw a cube here, like this, normally whenever we have volumes of any kind, that would be a voxel, and inside of this cube lives a value of some kind. So we could think of that as anywhere in the cube equals, let's say, a value of 0.1, or whatever it might be, right? Well, 2D volumes are the same thing, except instead of using a cube, we just use a two-dimensional square. And anything within this two-dimensional square, again, is going to equal whatever value is inside of it. So in this case, we have color being stored inside of each one of these two-dimensional voxels. And the reason why we use two-dimensional voxels is because they are pretty much identical to what a pixel is. A pixel makes up all the digital images we see, and they are tiny two-dimensional squares. So that's why Houdini represents this as two-dimensional voxels. Hopefully that makes sense. Now, this field right here doesn't have a name by default. So the next thing that I do is I name our volume ink vol. You can name that whatever you want, but it's just handy to name your volumes as you go along. Then right here we have a time shift. We take the current frame plus 1. So we take this and we take one frame ahead, and that becomes the ingredients for the texture optical flow node that we see right here. And what this now does is it looks at the difference between the pixel values, and wherever things change the most, it is going to create these flow fields that create XYZ vectors in that direction. But basically put, we now have 3 2D volumes that basically act as velocity in X, Y, and Z. If we then take this velocity and we apply it to, let's just say, this grid of points. So here I have a grid and I just scattered a bunch of points, right? If we take that, we can use an attribute from volume. We'll take our flow and turn that into a point attribute. We'll then use this point wrangle to advect our position by flow, and I divide by 24 because velocity describes where something will be in 1 second. So by dividing by 24, it basically just makes it work for this current frame. And as we can see, now these points are following the motion of our video footage, which is really awesome. But that's the main idea. We take images, we get velocity, and we can use that in some kind of way. Now, where things get interesting is how you apply this to an object or to some kind of project that you're working on. These velocity vectors are awesome, but it's not obvious on how you might use them in a practical way. So now let's take a look at our tree dude and see if we can get these velocity vectors to drive something along the surface of our tree guy. Let's now strategize a game plan before we dive into the details. So first of all, we need to apply this video footage to the surface of our model. And that needs to live on the model's UVs. Because the next thing we'll do is we'll take our model and transform that into UV space. Now, UVs are just position coordinates. So if I take our mesh's position here and I set it equal to the UV coordinates, I can basically take our model and unwrap it into a square. Once it's in that square, it's much easier to then work with 2D volumes. So we can run optical flow based on that. And then once we have our 2D volumes, we'll transfer that back onto the points that were transformed into UV space. And then we can copy those new velocities back over to the original mesh. Now, once we have interesting velocities along the points of our mesh here, what we can do is we can rasterize that into a velocity volume that then goes into a particle simulation and moves the particles based on those velocity volumes values. Once we have that, we also need to keep our particles attached to the surface. So for that, I'll use a SOP solver and a ray SOP to make sure that the points stick to the mesh at every single step. And then once we have our particles, we then can instance geometry to those particles and orient them along the surface so it looks like we have these mushrooms running along right here. That's the gist of how this all comes together. Now, obviously there's a lot of steps to this, so that's why I wanted to outline this. But let's go back to the beginning and talk about our video footage and getting that applied to the UVs of our tree dude. We'll need a couple things to get this working. Number one, we need interesting video footage. I just went here to elements.envato.com. You can find stock footage on there or any stock footage website you like. Or better yet, you can just take video yourself of something. And we need to turn this into a square crop instead of a 16:9 crop. Most likely, these are not going to be in squares. And we need this to be in a square crop so that it works properly with other things we do down the road. Let me show you how that gets done. For this, I'll use DaVinci Resolve. You can download this for free if you'd like. On the bottom right, we have this little home section. And for our project, I'm going to right-click, say New Project, and I'm just going to make a new thing here, Ian Collab Footage Demo, as an example. So we have a brand new project, and I'm going to right-click up here, and I'm going to create a new timeline. Now, this is the important part. We want to uncheck the Use Project Settings, and we want to manually set the dimensions that we're looking for. In this case, I want to create a 2048 by 2048 texture. So that's going to give me the square crop right there. I'll hit Create, and then we're going to drag over our stock footage. So here we go. I'll just drag this over, and now we can see we have our stock footage right there, and I'm going to zoom in until this fits the crop. So we'll go about 1.8 right there. So now we have this kind of thing going on, which is great. Eventually, what we need to do is a triplanar projection onto the mesh. And so here we have our tree dude, and I've assigned this effects material over here. And if we go to this effects material, what I'm using is a triplanar, and feeding into that is our texture that we have right here. It doesn't look good here in the viewport, but if we do a triplanar onto this and we hit render, now these patterns are being applied to the surface. And just for fun, if we were to do video of this, we could see that now the video has been applied to the surface of our mesh. So that's where we're going with all of this. And in order to get a clean triplanar projection, you also need to be working with repeatable textures. So now back here in Resolve, in addition to getting a square crop, we need to turn this into a seamless texture so that the borders of these squares will blend nicely with each other. So to do that, there's a couple of things we need to consider. Number one is that when I move this around right now, we can see that it hasn't applied the square crop yet. So what I'm going to do is set our in with I and O for out, and I'm going to just send out a sequence of images so that we can then bake in our crop. For this, I'm going to send out TIFF images. The file name here is square crop bake, and then I just made a folder within my project directory to save those TIFFs out. So we'll do that, add to render queue, and then we will bake out this video footage into TIFF images. Once we have our TIFF images right here, I'll then highlight all of them and drag them back onto the timeline. Now, when I position this left and right, you can see that we've baked in that square crop. So now, with that being the case, I can turn this into a repeatable texture. The way it works is that we'll take half of our width in X, Y, and Z, so that's 1024, and we're going to offset everything so that eventually we have a cross section of all of our images. These are the seams that we're trying to fix right here. So we'll need to copy this over 4 times until we have a cross section of everything. I'll go ahead and do that real fast. And now we should see something like this. You should be able to see these seams clearly now. And if we use a clone tool, we can essentially feather out these interaction zones. And when we're triplanar projecting, we won't see these harsh lines appearing anywhere on the mesh. So let's now highlight all of this. I'm going to right click and I'm going to create a compound clip that allows us to use the clone brush on everything. So for this, I will call it our repeatable compound clip. There we go. Then in Fusion, down here, I'm going to set down a paint node. So Shift spacebar, keyword is paint. We'll then plug this into the yellow input right here, and we'll go right there. And on this paint tool, I can then do a few things to get this clone brush working. So first of all, we want to go here and select the clone option. Then we also want to take this stroke duration for, let's say, 500 frames so that it doesn't disappear at any point along the way. This is how long the clone brush works before it disappears. So I just set that to a high number so that we always have it. Then I'll turn up the size of my brush, I'll turn up the softness, and then to sample this, we just hold down Alt and we start painting out areas like so. It's not going to look that great, but we're just trying to prevent these harsh lines from appearing. When it goes to triplanar project, it's going to be very difficult to really tell that this is not a repeating section. So we just need to go in areas like this and take care of those seams little by little. Once everything's looking good, I now want to bake again. This time this will apply all of our clone brush changes. So again, I, O, and again, we're going to save out TIFFs. All right, I dragged it back in, and one more time, we are going to offset everything by 1024 So that way we are back to where we started again. So now when everything is back to where it should be, we have this. All of those seams are taken care of now. And if there's any other areas that are an issue, like sometimes you have these little zones up here, you can just brush that up by doing some more clone brushing. But in this case, it looks pretty good. So this is now going to be the final thing that we export, again as TIFFs, and that's what we're going to bring into our triplanar projection within Houdini. Now in Houdini, we are ready to use our triplanar projection with that TIFF sequence to make it all happen. So to load that in, we just browse for those images and then make sure that you have this frame range turned on. You should see it go from 1 to 400 or however many frames you may have. And if the range is not starting at 1, then double check the naming of your files. In DaVinci, there's an option to have it start at 1. So just double check that if you're not seeing the right range appear right here. But that ought to bring it into our texture node. It goes to triplanar, and then at render time, we see everything being applied to the model. There's just one problem though. We can't take that data as it is right now and make it work with Optical Flow. We need all of this to be in UV space so that we can flatten things out and utilize our 2D voxels. So in order to make that happen, now we need to bake this signal into a texture map. In Karma, you may have a difficult time doing this. As of recording, Karma still struggles quite heavily with baking anything out to textures. It may be doable, but you might have to hack it a little bit. Depending on when you're watching this, maybe there's a solution that's come out that's helped with this, but double check online, look it up if you're using Karma to bake out a texture map from there. With Redshift though, it's very easy. We just go here to the Redshift ROP, we say render maps, we turn that on, we select our tree dude right here, and then if there's any lights that need to be turned off or any objects that need to be hidden, we can go here to this Objects tab and say whatever we want to include here with the texture bake. So if we do that, and then we go back to our tree dude here, and we have our material set up like this, so that our triplanar just goes directly to the surface out, when we render this out in the Redshift render view, we should see this. Now we can see that our triplanar signal is baked to our UVs. We can then save this out as an image, and this will be the ingredients for our Optical Flow node. So now let's save this out. It takes about 8 seconds to render one frame, but we'll save this out as a TIFF sequence, and then we'll load that into a file cop, and that will become the ingredients for our Optical Flow. So now we'll go through the workflow that I showed you earlier, where we just load in the CopNet, we bring this forward one frame in the future, and we use the Optical Flow to get us this sort of volume again. Once we have that, we then need to take our model, our tree dude, and convert him over to UV space so that his points overlap the locations we have here with our 2D voxel texture. So to bring him into UV space, start by creating a point split node, and we're going to split by UV. Then, once you do that, you want to promote UV from a vertex attribute to a point attribute, and that allows us to use a point wrangle to then say that our position is equal to our UV. And just for fun, if we want to see what's happening here visually, we go from our 3D model and we're flattening this down into parametric UV space. So that's what we're doing here. The only issue is that this doesn't line up with the location of our Optical Flow. So I take this transform node here to make them line up. You take this down in half and then you move it in the X and Y direction by 0.5. That will get this to perfectly line up with our points from our mesh. Then we can do the attribute from volume. This will bring over the velocity values from our optical flow, and we can use that to then reapply it back to our model. So with the attribute copy, because the point numbers over here on these points are identical to the points on our original mesh, the attribute copy will do a one-to-one match between these two sets of points. And this allows us to bring over our flow attribute. I also made this flow mag attribute that just takes the length of our velocity vector. So that's essentially measuring how fast is something going, and that's going to be a float attribute that we may want to use in the future. We may not. It's just nice to have just in case. So now we have velocity vectors on here, and it's time to use those velocity vectors in a particle simulation to move points around. From here, things act as they normally would whenever you make a particle simulation. So on the right-hand side, I create my pop sim points. These are the source points for the simulation. For that, I just smoothed out the normals a little bit, and then I scattered some points. I used the flow mag as the density attribute to give us an interesting pattern to the scatter. So anywhere things are moving really fast, I'm spawning more points in those areas. And then with this, I just normalize our normal vectors. I set a group and I cache this out. On the left-hand side, this is where I take the flow attributes and I adjust the length here so that we don't have any velocities that are going more than 5 meters per second. So this prevents our velocities from getting too intense, just in case there's some issue with that. I then rasterize this flow attribute into a volume right here, so that now if I middle mouse, we have flow. I have this at about 838,000 voxels. That's a good amount to aim for, I'd say. And then we name this field into velocity and cache that out. Going into the solver, I wanted the points to start at the bottom and then crawl their way up the model on top of following the direction of our optical flow. So to accomplish that, I brought in our points and I just used this delete SOP to isolate the points to one section along our tree dude. From there, my plan is to spawn points from down here and then move them up in the Y direction as they follow the patterns of the volumes that we have right here. So there's really two forces doing this. It's the optical flow forces, and we're also going to have a pop force that makes them go up and crawl up the model. So now in the PopNet, we source in our points right there. For this, I just set the mode here to points, and I'm going at about 10,000 points per second. Then I use this pop advect by volumes. That's going to grab our optical field velocity. So that's grabbing our volume right here. I'm going to say update velocity, and we also need to take our velocity blend here and set it to 1 divided by the frames per second, which is 24 frames per second. That's going to give us an accurate location or an accurate velocity here for our optical flow. Then on the pop force, I'm going to take this up in the Y direction. I have this animated so that it goes up in the Y direction and then it goes down once I'm happy with the points reaching the top of the model. So this will go up for most of the simulation and then go down. And then last but not least, to get the points to stick to the mesh at every single frame. So here I'm bringing in the tree dude, and the points from the simulation come in on this side, and the ray SOP is going to take the minimum distance from the point to the model and attach it. So basically, all of these forces will move the points around, and then the ray SOP will just bring it back to the surface. That all goes through the pop solver, and by the end of it, we clean up attributes we don't need, and we end up with a particle simulation that looks pretty cool. Now as I go forward, we can see that we have our particles and they're all following along the surface and moving in those interesting directions that have been decided by Optical Flow. Then for rendering, I just instance out all of these different mushrooms. So here I have them all laid out. I set a name for each of the mushrooms. I then run a for each loop on each one of these mushrooms, and I bring them to the origin so that they are right here, ready to be instanced. I then bring them down, and I also pack them into packed objects. Don't forget to bring the name along with that, by the way, when you pack, because then that information can go over here to our points. There's our simulation points. I then use the scatter, align, and the attribute from pieces node to create all the attributes necessary for instancing. This then can go here to the copy to points, and that's the main logic that goes behind instancing one mushroom per points. We can randomize the scale, randomize the rotation for each mushroom, and we have all the controls we need with scatter, align, and the attribute from pieces. I have a few more nodes here, and all I'm really doing with this is adding an interesting bit of color to everything. So here I bring in our tree dude. I then apply the maps that we baked out. So these are the triplanar maps that got baked onto our UVs. I'll then average out the color between the current frame, 2 frames ahead, and 4 frames ahead. That can go to a blend shape node, and by doing that, it just averages the colors out amongst the current frame and 4 frames in the future. This will help prevent flickering in the color. So basically, I want these mushrooms to light up over time, and this will prevent that light up effect from being too stroby, essentially. So I do that. I blur out color even more with the smooth node, and then that goes into this attribute transfer to the instance points. So the colors here on the points, eventually that goes into the shader for the mushrooms, and each mushroom has its own shader. And here all I do is I bring color in as an attribute, and that adds into the original color for the texture. So here's the texture map. I just add a little bit of color to that, and that makes our mushrooms kind of glow over time. That all goes to the shader. I have some other shading nodes here just for adding bump map and just, normal shader things for each mushroom. And then all of this goes to copy to points, cache it out. This is what goes to render. And when it's all said and done, we end up with this. So here we go. We have the mushrooms. They're moving along the surface. Every now and then you'll see the triplanar projection colors add a little bit of brightness to the mushrooms. But the real interesting thing about this is the animation, the motion that these mushrooms have. It's way more organic than what you would have otherwise, and that's really the main thing to take from this particular tutorial. Now, I'm sure all of you have been asking, Tyler, what's up with the Hawaiian shirt? Well, the reason why I'm wearing this awesome flower shirt is because it pays homage to Ian's Patreon. Ian has a fantastic Patreon that everyone should check out. It's extremely affordable, and you'll find all kinds of great tutorials that get into instancing, floral patterns. If this kind of style is something that you like, you definitely want to check out his Patreon and support this channel. Thank you so much. Again, my name is Tyler from CG Forge, and I hope you have a great day.